Okay, good morning, ladies and gentlemen. Let's continue with chapter 4. It is about transient heat conduction. In the previous lecture, we have showed the derivation of the temperature distribution as a function of time for a lumped system approach. Now, what a lumped system approach is going to become more clear to you. That is the equation where B is equal to that. However, you will later on see that this equation can also be written as theta, which is the non-dimensionalized temperature. Be a little bit patient, we're going to get to it just now, is equal to e to the minus the Biot number multiplied by the Fourier number. So you can also express it like that. The non-dimensionalized temperature is equal to e to the minus dt. So, one of the biggest questions that students have and that students really battle with is when they can use this approach. Because if you look at this chapter, it is by far the simplest possibilities of how you can try to solve a problem. It's simpler, not a lot of work, so we all would like to prefer some simple solutions. So the question is now, what criteria do we use? And to get to a criteria, we are first going to define a so-called characteristic length. Characteristic length of this body, an arbitrary body that we set as a mass m, a Cp, a density, a k, etc., and it is exposed to an environment, T infinite, and a heat transfer coefficient. Now, how we calculate the characteristic length is to say it is equal to the volume divided by the surface area. And that the Biot number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. And in general, if we have a problem that we want to solve, there are two ways of solving it. The one way is using paragraph 4.1 by saying it is a lumped system, and then the others, 4.2 and all the others, which are much more work, much more complicated, and in general, I think about 0.01% of all problems can actually be solved with a lumped system approach. All the others actually doesn't fall under the lumped system approach. So the question now is it, well, okay, if that is the case, is it totally useless? Not quite. There are still many cases that can be solved with a lumped system approach. And for the lumped system approach to be valid, the Biot number must be smaller than 0.1. The Biot number must be smaller than 0.1. Why? What is the reason for that? The reason for this is if we look at this body, then in principle there's a thermal resistance and there is a convective resistance. And the Biot number, by definition, is equal to the heat transfer rate of the conduction divided by the heat transfer rate of the convection. It's convection divided by conduction. Convection divided by conduction. And we are not going to go through the derivation, but it is from this that we can actually indicate it is actually the resistance of convection to conduction. the resistance of those two terms. So in general, if we go and try different solutions, we will get an exact solution if the Biot number is equal to 0. And for all the others, if the Biot number is typically smaller than 0.1, we can expect a solution accuracy of maybe 5–10% or something like that. Now, except for the fact that it is very simple to go and calculate the Biot number, and based on the value of 0.1 smaller or larger, just continue with all the calculations, it is also just as important that we actually understand where does this come from, and why can we only use it if the Biot number is so small. Coming back to this equation of the Biot number, which is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity, then generally there are three things that we can use to determine if the Biot number is very small. Firstly, if we look at the heat transfer coefficient, in chapter 1, you have looked at convection heat transfer, and you will see that the heat transfer coefficient can vary from very low values of approximately 5 to 10,000. So the first criteria is if we want this thing to be small, the smaller the heat transfer coefficient, the smaller the Biot number will be. So in general, it is applications where we have natural convection. Natural convection, I heat this piece of chalk and I wait for it to cool down, and it only occurs, the flow around it only occurs because of the density differences. So that's the one reason. The other reason is when the characteristic length is small. So small geometries. And then the last one is when the thermal conductivity K is very high. So in general, if you have a problem where heat transfer occurs in natural convection, it's a small geometry, and the thermal conductivity is very high, then that would be an excellent example that can be solved with the Biot number. Just to give you an indication of typical values of K, thermal conductivity of K can typically vary from about 385 watts per meter Kelvin, and that would be for copper. And in your tables A4 to A6, you will get many more values. For silver, it is 4 to 9. What material has the highest thermal conductivity? Highest thermal conductivity is carbon, or diamond, sorry, which is made from pure carbon. And then small values of thermal conductivity is, for example, wood with a value of 0.16, and cork in a wine bottle 0.039. Just order of magnitude values so that you can see which bodies we can typically consideration and that will qualify for small Biot numbers. So we can see bodies with high thermal conductivities, copper, silver, diamond, etc. All of them are very suitable problems to be solved with the Biot number approach. Specifically a diamond also, the geometry is very low, and if the cooling occurs in the natural environment, the heat transfer coefficient will be low, typical value of about 5 to 10. So bodies like that would be excellent examples for using the lump system approach. But let's do an example. It is problem 4.13 in your textbook. And the example that we're going to consider is that of a brick. And this brick has dimensions of 203 millimeters, 102, and 75 millimeters. Typical brick. Initially, it was in the kiln with a temperature of 1,100 degrees Celsius. It was heated in a kiln, 1,100 degrees Celsius. The density is equal to 1,920 kilograms per cubic meter. The CP value is equal to 790 joules per kilogram degrees Celsius. The thermal conductivity K is equal to 0.9 watts per meter Kelvin. And this brick is taken out at T equals 0, and it is exposed to the environment, which is at a temperature of 30 degrees Celsius, a heat transfer coefficient of 5 watts per square meter degrees Celsius, and we would like to know how long will it take for the brick temperature to reach 35 degrees Celsius. 5 degrees Celsius, warmer than that of the ambient air. Do you all understand the problem? It's a brick, 203 millimeters, 102 and 57 millimeters. It was baked. The initial temperature in it is 1,100 degrees Celsius, and this temperature is the temperature everywhere, so it's the uniform temperature. The properties of the brick is 1,920 kilograms per cubic meter. The CP value is 790, the thermal conductivity 0.9. The outside temperature is at 30, the heat transfer coefficient is equal to 5, and we have to go and calculate how long will it take before this brick cools down to a temperature of 35 degrees Celsius. You all understand the problem? Okay. So if we now look at the approach that we need to follow, we can see there's the equation that we need to use, but the problem is now, can we use the lump system approach? Would it be a valid approach for this problem? How do we do that? Well, by calculating the Biot number. If the Biot number is smaller than 0.1, not percent, the Biot number is smaller than 0.1, then we can use the lump system approach. Now, to do that, we first have to determine the characteristic length, and the characteristic length is the volume divided by the surface area. So let's start with this characteristic length. It is equal to the volume divided by the surface area. Okay, the volume of the brick is the 3 dimensions. It's 0.203 multiplied by 0.102 multiplied by 0.057. Okay? Then we have to divide it by the surface area. Let's start with this surface area here. So that is equal to 0.102 multiplied by 0.203. And there will be 2 of them. It will be at the top as well as in the bottom. So that would be the first surface area. Now let's use this one, the surface area there, which is equal to 0.102 multiplied by 0.057. And again, there are 2 of them, at the front and at the back. There it is. plus the last surface area, which is now this area here, which is 0.102 multiplied by 0.057, and again there are two of them. Do you agree? You happy with that?
So we use 0.102 times 0.0575.
Oh, sorry. This area, okay, so it's this area, so it's that distance, 0.057 multiplied by 0.102. Is that right? I see you shake your heads. Okay. I'm doing something silly here. I'm standing too close to the board. I can't see, but you can go and fix it. So it is just the surfaces, the 6 surface areas. Okay, I see. Is that right? Okay. If it's still not right, please just go and fix it at home. In any case, if we now go through the calculation, the characteristic length is equal to 0.01549 meters. Now we can calculate the Biot number. The Biot number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity, which is equal to 5 multiplied by 0.01549 divided by 0.9, and that is equal to 0.0861, okay, which is smaller than 0.1. Therefore, we can say lump system is valid. It would be a valid methodology to solve the temperature with this very simple equation. Okay. So now that we've got the green light, let's calculate the value of B. The value of B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume and Cp. And if you look careful, you will see that here we've got the volume divided by the surface area, and the volume divided by the surface area is the characteristic length. Okay, so we can write this also as it's the heat transfer coefficient divided by rho, the characteristic length, and K. You agree? You can go and put in the values. Yeah, I'm sorry. You are still going to figure out that sometimes there's a huge difference between what I say, what I mean, and what I write. But by the end of the semester, you'll be able to figure it out. Yep. Sorry? Okay. Fine now? Okay. Right, so the heat transfer coefficient is 5. The density is 1,920. The characteristic length is 0.01549. And the Cp value is 790. And if we go and calculate that, then it is equal to 2.128 multiplied by 10 to the minus 4. And if I'm not mistaken, I think actually it has units of per second. But now we can go to this equation that we've derived with the previous lecture, which says that the temperature difference divided by the initial temperature minus T infinite, which is the non-dimensionalized temperature, we're going to address that just now, is equal to E to the minus 2.128 multiplied by 10 to the, let me write it first, as minus BT. I'm too much of a hurry now. Okay, now let's put in the temperatures. We want to know how long it is going to take for the temperature to reach 35. Take note, those three are the constants. The only one that changes as a function of time is this temperature there. So we want to know how long will it take to reach a temperature of 35. The environment is at a temperature of 30. The initial temperature of the brick was 1100, and the environment temperature again is 30, is equal to E to the minus 2.128 multiplied by 10 to the minus 4 multiplied by T. T is the only unknown. You know you need to take the ln to get rid of it, and then you can solve that the time is equal to 2.522 multiplied by 10 to the 4 seconds, and that is equal to 7 hours. So it will take 7 hours for the brick's temperature to decrease from 1100 degrees Celsius to 35. Simple? Okay, there's not going to be much more simpler in this course than this part of the work. Okay, but again, I want to come back to this very important principle. It has to do with the resistance. Remember resistance with the previous lecture? If there's an emergency and 3 of the 4 doors are locked, and all of you have to exit through this door, all of you will not be able to exit through it in 3 seconds. Okay, because there's lots of resistance. You cannot move very quickly. However, once you are outside, the outside resistance is very small. So, with this type of problem, it is about the relative values of the resistances. Now, we are not going to waste time on it, but if I look at this brick now, and I would go and look at this resistance versus the resistance of the convection, just to give you an idea, if I would draw it to scale, do you see that? If that is 1 millimeter, okay, then the other resistance of the convection would be 3,813 times more. So if this is 1 millimeter, then this resistance will be about 1, 2, 3, almost 4 meters. That's how big is the resistance. So the reason why this problem can be solved with a lump system is because there's no resistance on the inside, relative to the outside. It then also means that if we look at the temperature as a function of time, for, let's choose a 0.1 there in the center, a 0.2 offset from the center, and then a 0.3 on the surface. If we look at the temperature of 0.1, it would do something like that. It would start with 1,100, and then it should approach, after a long time, it should approach a temperature of 30. So that would be the solution at 0.1. However, the solution at point 2 will fall on the same line as well as point 3. All of them gives the same solution. That is what the lumped system approach means. So this is lumped. Okay. For most other cases that we are interested in, the temperature distribution, if that is the temperature variation of point 1, then most probably the temperature variation at point 2 will do something like that, and at point 3 something like that. So it will differ from point to point in the body. You understand that? So that is the limitation of the lumped system approach. Let's continue with paragraph 4.2. Paragraph 4.2 is we are putting this behind us, all this easy work, and we start getting some better solutions. And in paragraph 4.2, it has to do with, firstly, the large plane wall, second, long cylinders, and third, spheres. So those will be the 3 different geometries that is considered in paragraph 4.2. If we show them schematically, then this would typically be a plane wall. So it would be very long, and that is the center, the geometry. And this body will be at a temperature Ti everywhere at T equals 0. Ti, that would be the temperature everywhere in the body at T equals 0. And what is very important is that they actually put down there for you the coordinate system that shows X, and very importantly, take note, it says this distance is equal to L. Okay. This distance L is not the LC of the lumped system. It's a different L. Okay. Do not mix the two. So that's the first type of body, a large plane wall. An example of the heat transfer through a large plane wall can be one of the walls of this venue. You would like to know how much heat transfer goes through it. Then another type is the long cylinder. There's the long cylinder, again like that. And again, they give the coordinate system and they say that is equal to R0. So you cannot go and calculate the characteristic length of that cylinder using the criteria for a lumped system. The lumped system criteria is only reserved for the lumped system. And for all of them, we have on the outside the environment temperature and the heat transfer on the left and the right. And the same with this problem. TO, the heat transfer coefficient and the heat transfer coefficient. And again, the temperatures inside the body is uniformly equal to Ti and at T equals 0. And then the third type is the sphere. The sphere, again, that is equal to R, and that radius is equal to R0. And again, the temperature everywhere is uniform at a temperature Ti. And on the outside, we've got the environment temperature and the heat transfer coefficient all uniformly spread around the cylinder. So what we're going to do here is we want an analytical solution for the temperature distribution through these three simple geometries. Now the one that is written out in your textbook is only this one. But if you go and look in literature, there are similar solutions for the cylinder and the sphere. And it is a little bit complicated. So you're going to start with a differential equation that's going to come from the energy equation, and you are deriving it at the moment in terms of the Navier-Stokes equations. And this equation is going to say that the temperature distribution, the second order temperature distribution, is equal to 1 divided by alpha multiplied by dt. So I've got two t's. The one is the temperature, the capital T, and the small t is a function of time. Right, so that is the equation, and it looks like a very simple equation, and it is a simple equation. If you think of the full energy equation, you will know that there are actually also in it the other dimensions in the y and in the z directions. We are assuming the heat transfer only in one direction going through the body, so that is why the others are thrown away, and that is then the equation that you end up with. So alpha, for in case you can't remember, is the thermal diffusivity, and that is equal to K divided by rho Cp. The thermal diffusivity, so it is all the property characteristics which are being put into one term. Right, so that is the differential equation, and then there are certain boundary conditions and initial conditions. So if we have a problem like this, we know, for example, if this temperature is higher than that temperature, then in the beginning the temperature is going to do something like that, but then it is going to reduce parabolically, and you're going to have with time a temperature distribution, something like that. And to solve that, one of the very important boundary conditions is that the gradient there should be equal to 0. So we make use of that boundary condition, we make use of the initial conditions. The initial conditions is the temperature Ti is equal to, or the temperature is equal to Ti, etc. Now what is the real problem? Very simple equation, but very complicated to solve. Now to solve it, people realized that one of the problems is that the temperature is a function of x, L, time, thermal conductivity, alpha, the heat transfer coefficient, Ti and T0. So there are 8 variables, which makes it very complicated to solve. So now if you've got things which are so complicated, you try to make it simpler. And how they make it simpler is they non-dimensionalized some of these terms. And the non-dimensionalized temperatures are, firstly, theta, which is the non-dimensionalized temperature distribution. So that is the dimensionless, let me rather say the dimensionless. The dimensionless, firstly, temperature. The temperature, just go back to the lump system approach. You see this temperature, we set is equal to theta, and if you go and look at it, you will see that theta can only vary between 0 and 1. Okay? Vary only between 0 and 1. Then there's also the non-dimensionalized position x, which is equal to small x divided by L. And remember, we are busy with this solution here, one of the plane wall. We are not doing the other two at the moment. That is in literature. So this one is position. Then we have the Fourier number, which is written as tau, which is equal to alpha t divided by L squared, can be written as tau or F0, the Fourier number. And that gives us an indication of the non-dimensionalized time. And the Biot number, again, is also here. It is equal to K divided by HL. However, the L, I can't say it enough, the L is this L. It is not the one that you're going to calculate using the lump system approach. So, why did we all do that? Well, the reason is very simple, because now we can write the non-dimensionalized time as a function of the position, the Biot number, and the Fourier number. So now we only have 3 variables, where previously there were 8. Right, now to solve this, there are 2 possibilities. The one is, which is in the first part of 4.1, is a sort of an exact equation. And then there are approximate analytical equations as well as graphical solutions. And the graphical solutions are called Heisler charts, in recognition for Professor Heisler, who generated them. So there's an exact solutions and there are approximate solutions. That is, all the details are given in your textbook and all the details on this side also. Right, now the results has been summarized in table 4.1. Now this table is very important. Okay? You will see that it gives the solution of the plane wall. That's the solution for it. There's the solution for the cylinder, and there's the solution for the sphere. So they are different. Let's look, for example, at the one of the plane wall. The first one is, it shows table 4.1. It shows the solution for the plane wall, the cylinder, as well as the sphere. And it shows the solution as the non-dimensionalized temperature is the sum of n equal 1 to infinite, and in that equations occur lambda n, there's a tau, there's an x, and then here it gives the so-called roots, which are lambda n ton of lambda n is equal to the Biot number. How did they get there? They made use of the method of separation of variables. And together with that, they've identified the characteristic equation, the eigenfunctions, the eigenvalues, etc., etc. Okay. Now the plane wall is the simplest of all of them. It is then followed by the solution for the non-dimensionalized temperature. And then you will see also those things, but now jumps out a J1 and a J0. Those are the so-called Bessel functions. I don't know if you've done it in mathematics. The Bessel functions, and then there's also the solution for the sphere. Now that table is going to be a very important table for you in the test and exams. But there are a few things that students keep on missing. And that is in the small print underneath the table, in the small print, there are very, very important information. It defines, for example, the Biot number. The Biot number should be calculated as HL divided by K, and it specifically mentions there that the L should be the characteristic length, this one, and not the one of the lump system. While for the cylinder, it would typically be R0, and for the sphere, it will also be R0. So it's very specific about it. Also in it, I'm going to read it to you. You need to highlight that in your textbook if I can give you advice. So underneath it says the non-dimensionalized temperature. Okay, it has been given on the board. It's the dimensionless temperature. The Biot number is equal to HL divided by K, or HR0 divided by K. The Biot number is given there as that equation, and the Fourier number and the J0 and J1 values, the Bessel functions for the first kind, are given in table 4.3. So, if you go and look a little bit further, you'll see that is typically the table that is being referred to. In table 4.2, gives the Biot number. Okay? So once you've got a Biot number, then you can get lambda 1 and A1. Do you see that? But be careful, don't use only the first two. The first two is valid for the plane wall. There it is. Okay. The second two is valid for the cylinder, and the last two is valid for the sphere. Okay, you see that? And then next to it is the Bessel functions, the solutions for that also. Ladies and gentlemen, do you have any questions? Are you with me? Yep.
Sorry, sir, back to the big question, where you showed the larger resistances on the outside, which is the convection. So, but that equation says more convection over more conduction. Wouldn't it be a
Which equation? This is, yeah, the Biot number is the ratio of convection to conduction. You can just go and check it. Yeah, I think this must be the other way around. It must be the conduction divided by convection, the ratio of the two. Okay. Okay. Now this looks very complicated. However, there is light in the tunnel. I don't think I hate you that much that in the exam I'm going to ask you to solve this, because you must imagine you're going to solve this for n equal 1, for n equal 2, n equal 3, and you will have to add all the solutions together. So it's a lot of work. Now fortunately, it has been found through experimentation that we only have to use one term. The first term is sufficient if the non-dimensionalized time is larger than 0.2. If the non-dimensionalized time is larger than 0.2, so this value, alpha t divided by L squared, if that is equal to 0.2, we only have to use the first term. And the first term solutions has also been summarized in your textbook. There it is. It's given, now it is being written as theta for the wall. Okay. And then the next one, the very special case where the non-dimensionalized time is non-dimensionalized distance is equal to 0. When will it be 0? That would be exactly in the center. So the next three equations is the non-dimensionalized temperature at the center. So at the center, there they are on the board, these three equations at the center, and those are the one-term solutions. You'll see it's much simpler than the one in table 4.1, and that is what we're going to use in the next period to solve a problem with. Any questions, ladies and gentlemen? Yep. Ladies and gentlemen, if you can just quiet down, please.
Are we assuming that we have convection and conduction only in the one direction and not going up?
Yes, only one-dimensional at this stage. I'm not aware that somebody could manage at this stage to solve it in two dimensions. So there are a few Nobel Prizes or Fields medals in mathematics to be won if you can solve some of these differential equations. That's kept many, many people busy for years and years and years to solve those equations. Right, ladies and gentlemen, thank you very much. Then I'll see you again next week.